The next lemma that I'm going to introduce is the lemma 3 in the book. Here, I would like to make every label in my video series to coincide with labels in the book, which makes it easier for you to compare the videos in here and the original proof in the book. So you may wonder where's lemma 1 and where's lemma 2. Lemma 1 and lemma 2 are actually in the previous section in the book, before the Kronecker theorem. And actually the lemma 3 is the first lemma in this section on Kronecker theorem in Castle's book. So lemma 3 states that, here is my reformulation of the statement in the book. Given A m by n matrix with real entries, let script m to be the set of vectors in Rm such that U transpose times AQ minus P is an integer for any P in Zn and Q in Zn. Then we have the following. First, this subset M of Rm is actually a subgroup of Zn. And second, the subgroup M is a free abelian group with the following basis. So M is a free abelian group with basis consisting of m integer vectors u1 to the us in Zm. So I should emphasize that they are in M, and M is a subset of Zm, such that up to changing the m rows of A. Remember, A is an m by n matrix, so A has m rows. We may assume that U1 is a vector of the form its components U11, U12, all the way through U1m. And U2 is a vector whose first component is equal to 0 and second component is U22 all the way to U2m. And U sub s is a vector whose first non-zero component is the s component, USS, all the way to USM. With UII is not equal to 0 for any I greater or equal to 1 less than or equal to s. And for those who know the theory of finitely generated abelian groups, S is called the rank of the abelian group M. So this lemma 3 tells you that this set, which encodes the information of this Diophantine object, is a free abelian group which has a basis like this up to changing the m rows of this matrix A. And this might also justify this why we use the letter U, because this looks like the upper triangular matrix. Okay, now let's prove this. the part 1 should be obvious to you. So why any vector in M must be integer valued? As a matter of fact, this is already shown in our key lemma above. In particular, this part. So by setting q equal to 0 and make p equal to e sub j, the jth canonical basis vector in Rm, we have u must be an integer vector. So for any u in M, I'm just going to copy the proof down in here, which shows that this u in M must be an integer vector. And it is also easy to see that this M is a subgroup, because if you take any u1 and u2 in M, you can easily see that u1 minus u2 is also in M, because the transpose of this difference u1 minus u2 multiplied by aq minus p is also an integer valued vector, because u1 and u2 satisfy the same condition. So this is obvious. So M is a subgroup of Zn. Okay, now let's prove the second part. We'll prove this by induction on the integer M, which is the dimension of the whole space. First of all, if M is equal to 0, or the script M defined above is trivial, then the statement number 2 is trivial, because this is a trivial abelian group, which is free by default. So now we assume that M is not 0. Now I would like to make an observation. The observation says permuting the order of coordinates of the vectors u in M is the same as permuting the M rows of the matrix A. And do you see why? This is because if you look at U transpose times AQ minus P for any P in Zm and Q in Zn, and in particular, you look at this part. This U transpose times A is equal to U1 dot dot Um times, now we write A as a block matrix consisting of row vectors A1 through Am. So this is equal to U1 times the row vector A1 plus um times the row vector am. And this is further equal to u sub sigma 1 times a sub sigma 1 plus u sub sig m times a sub sigma m for any sigma which is a permutation on the numbers 1 through m, namely a bijection from the set to itself. So this tells you the permutation of the components u1 through um is same as the permutation of the rows of a1 through am. And that is why we say up to changing the m rows of A, we may assume blah blah blah. In the statement number 2. And if you are super careful, you may wonder if we change the order of components in U, so this part, named the UTP, may also change. But remember, we are taking arbitrary P in ZM. We can always permute the components of P as well, which are actually all integers, and we will have arbitrary choice for that. So that won't change the outcome of the statement number 2. So subtlety mainly lies in here. Permuting the components of U will be same as permuting the rows of A. And with this understanding, we are able to proceed with the proof. So now, by permuting the order of coordinates, if necessary, we may suppose that there is a vector u1 with components u11, u12, all the way through u1m with u11 not equal to 0 in this subgroup M, which is an integer valued vector. And furthermore, we require that we choose u sub 1 such that u11, which is non-zero, has the absolute value the smallest possible, namely up to permuting the order of coordinates. We chose a vector u sub 1 whose first component is non-zero and at the same time has the smallest possible non-zero absolute value. We are able to do this because this is integer valued. Now we consider the set M prime of the vectors in M with the first component equal to 0. Then you can easily see that this M prime is also an abelian subgroup of Zm. And you can think of this as a subgroup of the product of 0 and Zm minus 1, which can be identified with just Zm minus 1. So now we apply the induction hypothesis to this M prime, which is considered as a subgroup of Zm m minus 1. Remember I said we are going to use the induction on this integer m. And by induction hypothesis, we assumed that the statement number 2 of our lemma 3 is already proved for m minus 1 or less. So, by applying the induction hypothesis to m prime, we have a basis u2 through us, which is a subset of m prime with u sub I equal to 0, 0, 0. The ith component is uii, and the last component is uim for I greater or equal to 2 less than or equal to s. So strictly speaking, we are consider m prime as a subset of 0 cross z raised to power m minus 1. So that there are really m components instead of m minus 1 components for u sub I. So that this u sub I for I greater or equal to 2 and less than or equal to s will still have the same number of components as u sub 1. And I should say basis of m prime. And here I should emphasize that uii is non-zero. Again, as I remarked earlier, this can be achieved by permuting the rows of A, the matrix A, as in here. Now we claim the vectors u sub 1, u sub 2 through u sub s form a basis for the abelian group, it's a free abelian group M. And now let's check this. First, for any v in M, remember this u1 has its first component non-zero. So there exists an integer a1 such that the absolute value of v1 minus a1 times u11 is strictly less than u11. Then, if you look at v prime, which is defined to be v minus a1 u1, we will have its first component equal to 0. Do you see why? This is because we have chosen u11 to be the integer whose absolute value is the smallest possible value for the first component of u1, which is non-zero. And now you get another vector v prime in M whose first component has an absolute value strictly less than u11. There's only one possible choice. That is, this guy must be equal to 0. Namely, this v1 prime is equal to 0. So this vector v1 is in this m prime we just defined. So this v prime can be expressed as the summation a2u2 plus the dou asus for a2 through as in Z. And this is same as saying that V can be written as a1u1 plus a2u2 plus the dou asus. Therefore, the Z-span of u1 through us is equal to this m. Now it remains to show that u1 through us are linearly independent over Z. Suppose that c1u1 plus c2u2 plus the dou cs us is equal to 0 for c1 through cs in Z. Since by our induction hypothesis that the first components of u2 through us are 0, well, the first component of u1 is not 0. We have immediately c1 equals to 0. So you can cross out this term and just look at the remaining term, which is equal to 0. However, by induction hypothesis, u2 through us is a basis of m prime over Z. This forces C2 through CS to be equal to 0. So C1 through CS are all equal to 0. And that shows that U1 through US are independent over Z linearly. And this verifies this claim, which proves this whole lemma. So we are done.